Hello. So now we're going to study the cross product, but in component form. So we know the cross product between vectors A and B in component form, or in non-component form, sorry, like in the normal form, we just write the basis vectors, we write the components A1, A2, A3. So this is the typical form in which one writes the cross product. If we perform this calculation of this determinant, then we'll arrive at the following. So this is done in the following way, just to remind you a little bit. If you want to calculate the determinant, then you must multiply this by this minor. Then let's do it in orange. Now you multiply this by this minor, and lastly, do it in gray. You multiply this by this minor. So the thing is this: we're going to perform this evaluation of this determinant. You do the following. You have to know what is the index of A1, A2, and A3. So for instance, the index of A1 is 1, 1. The index of A2 is 1, 2, and the index of A3 is 1, 3. This is important because we're going to multiply by this, but the minors here. We do the following. We go minus 1 to the 1 plus 1 times the first minor. Let's do this with the colors that we set up. So the first color we set up was blue. Let's do this in blue. So this is minus 1, 1 plus 1 times the first minor, the minor in blue that we set up to be A2, A3, B2, B3 times A1. Now, let's do it in orange for the second term. Actually, I think that the minor, I don't remember properly what the minor would be, I mean formally, but I don't think it's this determinant, but I think it's this, the minors of a determinant are the subdeterminants that arise when you eliminate a column and a row. Yeah, so probably it's this small determinant, because here we eliminate column 1 and row 1, and then we're left with this small determinant, which I think is called the minor. I just don't remember, so just don't take it for granted, and just do some research and see what's the formal notation for it. So now we'll do this. This is plus minus 1. The index for A2 will be 1, 2, so this is minus 1 to the 1 plus 2. And let's call it the minor for the meantime. So the minor that we're left with is A1, A3, B1, B3. Okay? So then, now what we're left with here, let's use color gray to just denote the third term, which is plus minus 1 to the 1 plus 3 times the minor A1, A2, B1, B2. And I will use black for the following. This minus 1 to the I plus A, which is actually what this is. This is minus 1 to the I plus J, where this one here is located in position I comma J of the matrix. You could in principle do this with to evaluate the determinant. You could do this with any of the rows I, so it doesn't have to be the first row, but it doesn't make sense for the definition of the cross product to do it with any of them, but only with the one where the basis vectors lie on. So I did forgot to just put the other basis vectors here. And then with this we have just the complete evaluation of the cross product using this determinant. And this minus 1 out of I plus J, what are they? So this one, if I plus J is even, this is plus 1. If it's odd, is minus 1. So the only one that is odd is this one, the one in orange. So this one here is minus 1, but these ones here are 1. This one here is 1, 2. So then from this we can surely say that we're going to evaluate determinant. Let's keep on using purple now. I change a lot of colors to enhance the contrast of the calculations. So then let's do the following. We have this, so then this is the first term, or the component 1 of the cross product will be the evaluation of this determinant, which is A2, A3, B2, B3. Each of the components is accompanied by its respective basis vector. So then now just pay attention to what I'm going to do here. This one is minus, so yeah, just for the meantime let's just write it explicitly: minus A1, A3, B1, V3, A2 plus A1, A2, B1, B2, A3. So if we keep on using this logic, we can just straightforward evaluate everything, or we can leave it in determinant form. It doesn't matter. So but for the purpose of this derivation, which is to actually come up with an expression in component form for the cross product, so I will expand all the determinants and I will do this. So the first one is A2 B3 minus A3 B2. Okay. This is component 1 of the cross product, which can denote like this. Now, minus A1 B3 inside minus A3 B1. Say to this will be component 2 of the cross product. Finally, plus A1 B2 minus A2 B1. And this of course will be component 3 of the cross product. So then now we know what are the components of the cross product? What we want to know, or at least what this derivation is about, is the following. So we kind of want to come up with an expression of this sort. We want to write A cross B, but we want to know what's its ith component, the ith component of this vector, let's say, or the kth component. Let's say component k. Okay, so then the big question is, what is this? Now we know what is component 1, component 2, and all of those from here. And we know that each component is a permutation of the individual components of vectors A and B. For instance, if you have, let's say, component 1 of A cross B is composed by the permutation of components 2 and 3 from vectors A and B. So then what we can guess is the following. We can guess this, that the kth component of this one will be, let's say, will be something like the difference between some other two components permuted and subtracted. So AJ BI. This will be the component. The component doesn't contain the vectors, because we express or we expand a vector as a component times its basis vector. So then we're just concerned here about the component. Now there's one thing here. How we're going to come up with something like this, or is this even right? So then we will use, for such a purpose, we will use something that's called the Levi, I think it's like the Civita Tensor Notation. I don't remember the spelling of this, so please just check it up yourself. I actually think that's how it's spelled, but I might be wrong as always. So then we're going to do this. There's a tensor notation that it says the following. If I have a tensor aijk, what is this equal to? So then this tensor aijk is equal to 1 when the permutation between ij and k is cyclic. Ij and k cyclic permutation is -1 when ij and k is non-cyclic, and is 0 when I is equal to j, or j is equal to k, or k is equal to I. So in that order of ideas, if I depart from I1, let's say E1, 2, 3, and I want to write an equality of, let's say, E something here, this will be a plus or a minus. So then the idea is, according to the way in which I permute 1, 2, and 3, I will pick up a minus or a sign. If it's a cyclic permutation, then I will pick up a plus. If it's a non-cyclic permutation, I will pick up a minus. So cyclic permutations mean this, that you just put this one up front like this. This is 3, 1, 2, and just put this one up front, and this is 2, 3, 1, and then again put this one up front to arrive here. 1, 2, 3. So then you arrive at the same sequence that you started with. So then pretty much a cyclic permutation, you can see it as this. It's going from 1 to 2 and from 2 to 3. Sorry. 3, 1. Then if you just interchange any neighboring indices in this Levi-Civita notation, then it would mean that you will pick up a minus sign, because interchanging any indices, it will break the cyclic property. So here if you interchange, let's say 2 and 3, then here instead you will get 3, 2, 1. And if you cyclically permute 3 to 1, you will never get back to this one. So then you have broken the cyclic property of indices 1, 2, 3, and then you will pick up a minus sign. So then, by knowing this and going back to the cross product, we can say the following. That component 1 of A cross B, that it can be written as A2, A3 minus A3, A2. This you can say that is the Levi-Civita tensor 2, 3, 1. Note that this is a cyclic permutation. I can obtain this very tensor from cyclically permuting the indices of the tensor 1, 2, 3. See? And then I write here A2. Oh, that's in red. Good. So this is 1, and then A2, A3. And then minus, if I want to pick up here a minus sign, I can do the following. I can just interchange 3 and 2 and write a plus, because this one itself is an anticyclic permutation. So this one will be like minus E1, 2, 3. See, and then I write times A3, A2. So then I can say that the term, or the component 1 of the cross product A cross B1, it can be written in the following way. It can be written as the summation of the permutation between N and M of E and M 1 A2 sorry, I'm writing this in now in terms of N and M, AN, AM. To show this, you can just span this and then write it in this way. You have AN, M1, AN, AM plus AM, N1, AM, oh sorry, this is a B, this is here a B, BN, and this is equal to the following. So you can write it like this. If you permute M and M here, you pick a minus sign, so you go N and M1, AN, BM minus AM Bn. For n equal to 2 and m equal to 3, then you obtain the following. You obtain that, just avoiding the summation, A cross B 1, so the component 1 of A cross B is just AN M1 AN BM. So this works fine for component 1. See, now what happens for component 2, which has the minus sign preceding it? So here component 2 has this minus sign here, so it's of course A1 B3 A3 B1, but with the minus sign up front. So then we will do the following. Let's try to just elaborate somewhat on that. So then component 2. So for component 2 of this thing, we will do this. So just a minute, that the pen's got stuck here. So for component 2, we will do this. So you have A cross B 2, which is equal to minus A1 B3 minus A3 B1. We can write this in the following way. So we can write this as A3 B1 minus A1 B3. This is equal to, let's write this tensor here, E3 1 2. This is actually a cyclic permutation of the tensor E1 2 3. So if I start with this, just by changing stuff, I will never pick up a minus sign. I will arrive here. If you just know, the only thing you have to do is just to put these 3 up front with cyclic permutation. Then what we do is just write A3B1. This minus, it will be taken care of if we permute 1 and 3. So this is E1 3 2. Note that always the component we're referring to goes in the last position of the indices of the tensor, and then here we write A1 B3, and we just write this as a summation on 1 and 3, or M and M. It depends on how just you want to do. Yeah, let's use letters. I think is less confusing. M and M. So this is here M. This is N. This is sorry. This is 2. This is AM. This is BN. And this is nothing but A cross B component 2, which says here because we're summing over the rest of the indices. And we can do just pretty much the same for the third component. So for component 3, we will have A cross B 3, which will be just A1 B2 minus A2 B1. This will be Levi-Civita tensor A1 2 3 A1 B2 plus A2 1 3 A2 B1, and as just mentioned earlier for component 1 and for component 2. This is just some summation over some indices that are permuted, which is mn a, sorry, this is 3 here, this is m, this is bn. Let me write it clearer here, maybe it wasn't clear enough. mn 3 am bn equal to the component 3 of the cross product. And in general, now we have seen the following. I want to use a fancy color for this. I don't know how fancy can I go here. So yeah, probably I'll just use blue. This light blue. So then the component K of a cross product is equal to the summation over the permutations of I and J of EIJ K of AIBJ. This is a very important formula. Extremely important formula for everything we do in this channel. So if you enjoy what we do in this channel for condensed matter physics and quantum mechanics, quantum field theory, statistical physics, this formula you should manage completely well, because I use it a lot in didactic theory, working with spinors, with effective action theory, deriving effective interactions in magnetism. So then this is very important, and I just one of the purposes of the channel is to actually not skip any calculation. So when I refer to any formula during my video lectures in this channel, I will always refer to a video